Right. Hello, everyone. Welcome to the High Voltage Seminar. This session is titled Isolated Gate Driver 101 from Installation Spec to End Equipment Requirements. This session is being presented by Wei Zhang, Applications Manager for Texas Instruments High Power Drivers. My name is Sean Alvarado, and I'll be the moderator for this session. All participants are muted in this session. Please use the chat function to ask a question and address it to everyone. We will be reserving 10 minutes at the end of the session to answer questions submitted in chat. Also, use the chat if you're having any problems hearing or seeing the presentation. With that, I'll hand it off to Wei to start the presentation.
Good morning, everyone. Thank you, Sean, for the introduction. Today, we are talking about isolated gate driver 101 from the installation spec to end equipment requirements. In this presentation, we have a few points that we want to address. We will discuss the fundamentals, and next we will discuss in the isolation specifications, verification, and how to verify them. And in the end, we're going to close it with examples and how do we utilize this knowledge into an end equipment system. Here we are discussing one example for server and telecom right here. And in the end, we're going to have questions and answers. Here is showing an example of the server and telecom from the AC line to the brick module in the telecom system. So you can see here, we have the AC line, we have the EMI filter, PFC. Now we're having an isolated DC to DC, which is quite popular, and the output is nominal 48 volts, but it can range in from 36 to 75 volts. In this case, I'm showing 60 volts, which handles majority of the case. And followed by this 48 volts bus, there will be a brick module, or we call it the brick converter, that is having a certain amount of isolation and also turning from 48 volts to the 3.3 volts, 5 volts, 9.6 volts, 12 volts, or even 48 volts, just with isolation. And why the isolation is required? I mean, in the multiple systems. And the first reason comes is safety. And there are a lot of other reasons, like, okay, you want to have a 400 volts, 48 volts with a turns ratio to maximize your equipment duty cycle. There are also signal communication, breaking the grounding loop to control the common mode noise, and also working for conditions where the bus voltage is higher than 600 volts, because the majority of the non-isolated driver having the junction working voltage up to 700 volts. If you want to working for 800 volts or even 1200 volts, the best choice is isolated driver, because isolation can handle high voltage. So, and the next one is performance high CMTI. So CMTI for non-ISO driver is roughly sitting less than 50 volts per nanosecond, but for ISO driver, the majority of the driver in our family is minimum 100 volts per nanosecond. And we are also working on the next generation, reaching to 200 volts per nanosecond. So which is really very significant improvement going from non-ISO to ISO for very high power density and high frequency applications. But nonetheless, all of this benefit, the first and the most important one is safety. And today we are discussing why and how and what about the safety and using for the power converter system. There are three types which are pretty popular using in a variety of applications. We know the optical based ISO driver, which is started from 1970s, the optical isolation technology. And starting from 2010, people are starting to work on next improved isolation technology like inductive and capacitive, which is commercialized roughly about after 2005. So it is relatively new, but have over 10 years of multiple generations of devices. You can see on the market about inductive isolated gate driver and capacitive isolated gate drivers. Going through the advantages of the three categories, you can see, the optical is very long history. It's been proven working very solid and have low emissions. Inductive and capacitive share a lot of common features because they are all silicon dioxide based isolation barrier. So you can see it is fast, it is low power, It is very high noise mu on the CMTI. It is very low channel skew. I mean, if you're looking at the optocoupler based, the part-to-part variation is most of the time sitting around 50 nanoseconds. And if you go to the inductive and the capacitive, the channels matching or skew is less than 5 nanoseconds. For sure, you can find very high performance and very expensive optocoupler, which can also reach in similar performance, but that will be either very lossy or very high cost. But for inductive and capacitive isolation, it is very common. It is most of the drivers can achieve similar performance and very low part-to-part or channel skew. But talking about inductive and capacitive isolation, what is the major difference? The major difference is the high working voltage. That is what TI is, having all the isolators, sensors, ISO drivers being built in this technology based upon. So that is a capacitive isolation, which offers you a very high working voltage. If you want okay, I'm working at 1,000 volts RMS over 40 years, here you go. You only have one choice, capacitive isolation. So going to the isolation grade, you have functional, basic, supplementary, double, reinforced. There's so many words. But what is the really difference between these two? For functional isolation, it is merely using for ground bouncing, high voltage. And or sometimes you want to handle some 700 volts or few hundred volts transient between two grounds. For example, the bus converter, you have 40 volts, which is pretty safe. You have 12 volts, it's pretty safe. But there will be some transients coming from the battery side, 40 volts battery side, which the transient is less than 1.5 kV. And for that scenario, okay, functional isolation will be fitting the best. But when it's coming to the safety, protect human safety in case a single level fails, you need double isolation. And what is reinforced isolation? Reinforced isolation in a single device, you can achieve the double isolation. So that is where the reinforced isolation comes. So in long story in short, functional isolation is really just for proper operation of the the circuit level performance. And for basic isolation, it is protecting some equipment. But for reinforced and double insulation, it's protecting the human. And here's an example, which I believe you see a lot of materials in TI.com or in Google, finding, oh, what is the construction, how is the high volt capacitor look in the isolated driver from TI. So you can see here, they have a transmitter die, left side die. You have the receiver die, which is the right die in the picture in the upper left. And you have some die to die distance, which is here is 600 micrometers. You also have we have two series capacitors, one in each die, and summing the distance through insulation together, we are reaching larger than 21 micrometer in terms of the distance through insulation. And every micrometer will handle over 500 volts. So you can see the capacity of the insulation is very, very strong. And that's why in our data sheet, we are reaching a 12.8 kV peak surge voltage, 8 kV peak transient, and most importantly, compared with the inductive isolation, you are seeing a 1.5 kV RMS working voltage, and across all the reinforced isolation gate drivers. And this is by far in the industry the top of the line. And for some extended package in TI, we call DWW, which is 14 millimeter Creepage, you can even work in a higher voltage because 1.6 volts kV RMS is required by the IEC standard. With 8 millimeter Creepage, you can only operate in up to 1.6 kV. So that's where, what is the magic number 1.5? Basically, the driver, the internal of the capacity can work in really high voltage, is really limited by the packaging. And what I'm talking is the Creepage distance. And going to the datasheet of the ISO gate drivers, you can find, okay, there's so many things. Just talking about isolation without regarding, to other electrical parameters which going to make it, making the driver function. But the isolation, you can see the CLR clearance. CPD, Creepage, DTI, distance through insulation. And you also see a lot of standards, UL 1577. Also, you also see DNVDE 0884-11-10. You also see IEC 6747-5-5. And also you see a lot of working this voltage parameter, VZIS, VZANT, and RZIS, CIO. So it's very, very intensive. And if you go into the parameters, if I'm new to the isolation, your head is spinning. So many parameters. What are they? What does it mean? What's the purpose of this parameter? So how do I really relate this one to my real application? And how do you guys, the semiconductor company, verify this parameter? What is, if it is being certified, what is being certified for? What are they testing? What is the difference of this standards? That is raising a lot of questions. And in this presentation, we're going to address them one by one. And but in the beginning, before you address this, what is the purpose of all these parameters? What do they serve the function? What do they trying to tell us? So here are at least a few of my best understanding. You see that, it is want to prove the electrical stresses, mechanical stresses, thermal and environmental influences. You want to make sure that, okay, the driver, the ISO driver or isolator have the capability for basic, supplementary, and reinforced insulation barrier to withstand all of these stresses. And that's what all of this parameter in the previous page showed for. Because the driver has to withstand electrical, have to withstand mechanical, have to withstand thermal, and also a lot of other environmental influences. Now we're coming to okay, we have so many parameters, but where that belongs to? Okay, what is it is for this component, or is it for the end equipment, or is it for some other supporting standards? So here is a very comprehensive. You may have a lot of information right here, but I'm going to help you start it out. In the category, we have component standards, which is just telling the component and nothing else. We also have the equipment standard where this component be used in, and also have some common supporting standard, which is we call IEC 60664. So go to this category, and for component, you see opto, you see magnetic, capacitive, you also saw some UL 1577, which is used for optocoupler and digital isolator. And for equipment, there are many equipments. You have server telecom in the information technology. You have for the control and lab, you have medical, you have motor drive, you have solar, you have so many end equipments. But all of this end equipment standard is based on the supporting standard, which is IEC 60664-1, which is insulation coordination for low voltage system up to 1.5 kV DC. So that is telling, okay, you have component, you have end equipment, and okay, you have some common library from IEC 60664 you can draw the knowledge from. And going to each category of this standard, you can find, okay, not all of these parameters being addressed in every standard. Only, for example, VD 0884-10-11 only addressing the TDDB. TDDB is time-dependent dielectric breakdown, which is telling how long this driver will operate and maintain its isolation in this working voltage. So you can see the differences between all of this category. And when it's talking about clearance, creepage, pollution degree, these are all system related, because inside the chip, it is pretty clean. There's no, the pollution degree for the IC internally is pollution degree number 1. So that can tell you basically structure of, okay, this parameter belong here, and what are they basically talking about. So we start from the first one, RIO and CIO. And this is also a very common question that customer is asking. If you go into the internal structure for the opto, for the inductive, for the capacitor, you can see because this is in the real world, you can, even in the optical, you can see the mode compound, you can see the junction to junction have capacitance. Even for inductive, you also have copper layer to copper layer through polymerized or silicon dioxide across the capacitor. So you have present here and there, and they are all summarized into RIO and CIO. And in the optical and capacitive, inductive isolation, you still have parasitic capacitance. Wherever you see two coppers, you are having a parasitic capacitance. And for sure, RIO is where you want making sure the voltage is being blocked from. Okay, they are tested with the given specification, and the resistance being measured at 500 volts in different temperature. So basically, this is a universal standard applied for every category. So CIO is the input-output capacitance, RIO is the input-output resistance. So that is telling, okay, in the real world, you can see what these parameters are telling from. And they also are changing from, let's see, T-safe is the safe temperature, which is 150 C, ambient max, and ambient. And the next one is the VISO and VIOTM. VISO is the maximum withstanding isolation AC voltage for 1 minute. And this has been spec for UL 1577, tested either using DC or AC. I mean, the new information here is most of the time you see, oh, it is AC, but it can be DC. It's fine. VIOTM is the maximum transient voltage, which is just the peak of the AC, which is 1.414 times the VISO. What is the purpose of VIOTM? It verifies the ability of the device to withstand the isolation test voltage under specified conditions for a short period. Okay, for this short period, it means, okay, in IEC, it's been telling 1 second or 2 seconds and 100% of this value, or maximum of 1.2 times of 1 minute rating. So in UL, it has been tested 1 second. You have to be applying a 1.2 times ratio. If you are 3 kV, you have to be testing a 3.6 kV for 1 second. And it's been tested for 25 degrees C. So for here, if I see a routine test means every part has to finish this test in the final test with automatic testing equipment before it reaches into your site. So it is a production tested item. And VIOWM and VIORM, you see here, it is not a routine test. It is a type test. That is pretty much verified by either TI internally or by the certification agency. So WMW is working voltage. It is really telling the long-term and the working voltage withstand capability. And the RM is a repetitive peak voltage, which is most of the time is 1.414 times of the working voltage. And most importantly, the degradation of the galvanic isolation depends normally on the peak voltage. And VRM is the repetitive voltage of absolute envelope of voltage over time. So this one is these two values are tied together. They are it matters with your long-term operation. It matters with your lifetime of the isolation barrier. Another one is the surge voltage. Surge voltage is a type test only. So what is type test? Type test is not routine test, which is being tested on every part in terms of the production. Type test is used for the certification, which the IEC, VDE, UL, they monitor the process of the manufacturer. So then, okay, it's been sampling test, it's been certified, it is not working for every part. So their surge voltage is the highest instantaneous value of the isolation voltage pulse with short time duration and a specified waveform shape. So what is the goal? The goal is to handling the lightning strike. This is pretty high. So you are working with the 1.5 kV system, but your surge voltage can be over 10 kV, and that is what the majority of the system requires, all the reinforced isolation working at least above surge voltage over 10 kV surge. So 10 kV surge and 1 kV working, there's a large gap. And this is just handle this very high short period. And in the certification, it is in 1 pulse per second. You have been tested for 50 consecutive surge pulses. That is for certification. Partial discharge. Partial discharge is majority is being used starting from the opto coupler. And the goal is to verify the performance of the insulation between input and output through the material, the mold compound, by measuring the partial discharge level under specified conditions. And you can see here, I show a equipment setup. The CA is your device under test. You have bypassing capacitor. You have partial discharge monitoring ZM, and you also have some filter. So the requirements, okay, under all the following tests that I'm going to introduce, it has to be less than 5 picocoulombs. And how do we test? And the partial discharge, there's a method A and method B1. So in method A, you can see here, it is having a charging profile. The charging profile is, okay, you start from 0, you ramping quickly to the VLTM, which is we introduced before, for 60 seconds, and to simulate occurrence of the transient over voltage. And then it goes to your working voltage. This repetitive working voltage based on times with the F. F is a coefficient, 1.6 for reinforced, 1.2 for basic. And for different subgroups that is being defined in the certification. So here, the QPD is measures the voltage is for 10 seconds. Over the 10 seconds, what is the total charge? Discharge right there. Method B1 is the only difference is, okay, it's a routine test. In compared with the method A is a certification test. Here this is method B1 is a routine test. So which means every part going to make sure your partial discharge under method B1 is not under 5 picocoulombs. And you can see here the major difference. The initial voltage is only for 1 second, but you have a different coefficient under the VRM, which is 1.875 for reinforced, 1.5 for VSO. I mean, if you see the F1, F2, F3, there are a lot of definition right there. So I give you some information. If you check the IEC 60664-1, it depends on one is environment factor, another is hysteresis factor, another safety factor, and also deviation factor from the normal voltage. So basically, it's been covering all the machine guardband, temperature guardband, or a lot of other guardband to make sure, okay, you are 100% test to make sure that your working voltage is being tested with the working voltage with also additional margin. And we'll see the real-time, real-world the waveform about how this is tested. I mean, here you go. You see it is AC test. It starts from 0, ramping to VLTM, and then you go into V2, which is your working voltage times the coefficient. So that's why you see in the standards or drawing line the DC or AC. So here is just drawing an example to have you vividly see what is being tested in the real scenario. And the next parameter I want to introduce is the time-dependent dielectric breakdown. As I mentioned before, only VDE have this parameter there. And the new released IEC for inductive and capacitive also introduced the TDDB also. And what is TDDB? TDDB is accelerated lifetime aging by testing the lifetime of the capacitive isolation in a very high voltage. Suppose in our data sheet, it is 1.5 kV RMS. And but in order to reach in the to certain failure rate, you have to taking the part really high to achieve the part. I mean, you have, for example, here you have 5,000 volts, you have 6,000 volts, and 7,000 volts. So make sure, okay, you have certain multiple parts, and then you recalculate your 1 ppm line, and then it goes to the 1.5 kV. You can see here with 1.5 kV, if you go to the lifetime, it is over 100 years. The reason why we put 1.5 kV is pretty much limited by the environment which the packaging, the isolation barrier has been seeking into, because the creepage distance for majority of the reinforced rubber is 80 millimeter creepage. The 80 millimeter Creepage by AC standard can only handle maximum of 1.6 kV under basic isolation. So that is okay, how do we validate the lifetime? Where do we spec? And how do we make sure that the driver is being handling in a proper situation so that it can meet the lifetime requirement? And if you see the majority of the TI isolator datasheet, all of them have this curve. And in which you can clearly tell, the driver not only can handle high voltage for short moment, it can also handle your working voltage for very long time. And that is only unique to TI. At this moment, I don't see any other competitors is being showing this lifetime curve in their datasheet. So the next one is the creepage distance and the clearance distance. So in the creepage distance along the surface, clearance distance along the air. So what I'm thinking, what I want to emphasize here is that when it's coming to the surface, it matters with the pollution degree, the humidity, and the condensation matters. But when it's going to the air, for the clearance, the only thing matters is air pressure. Oh, you are sitting at sea level. Oh, you are sitting at sea level plus 5,000 meters. And also the temperature also matters. So for each distance, they have been influenced for different parameters. And for creepage, it is tied to the RMS working voltage, tied to the pollution degree, tied to your surface material group. For clearance, it's tied to the temporary voltage, which is maybe high voltage transients, and also recurrent peak voltage that is going through the air. And if you go into over 2,000 meters, there will be a coefficient. For 5,000 meters, your coefficient is 1.48, which means, at sea level, you require 1 millimeter, but going to 5,000 meters, you're going to require 1.48. That is the parameter influences and also what it impacts. Next one is material group and the CTI. Material group is being dependent on the comparative index in the tracking index of CTI. And how do we test CTI? For all the detailed information, please go to IEC 60112. But here is really testing the maximum voltage VAC, and which in insulation material withstand 50 drops per 30 seconds, a drop to a contaminated water, which is having certain kind of chemical residue. And you have to make sure no tracking less than 0.5 amps. And it's being an accelerated simulation condition. As you can see here, CTA larger than 600 is material group 1, and the CTA less than 175 is material group 3B. So what I want to emphasize here, so the majority of TI driver is material group 1. I mean, I think I would say 99% in current scenario. But this is very high for the driver. The PCB which the driver has been sitting onto, 99% are material group 3A, unless you have other, very expensive PCB. Otherwise, the dominant PCB in the industry belongs to material group 3A. So which means you have a very good, very solid driver. You're sitting on a low material group, and who's going to decide the creepage distance? It will not be the driver. It will be limited by the PCB to meet the creepage and clearance requirement. So pollution degree. So pollution degree, what does pollution degree 1, 2, 3, 4 means? Here I give you some examples. In the pollution degree 1 is which means there's no conductive pollution, and pollution degree 2 where we are working in the office, in the lab. You're going to see some occasional condensation, but it's very rare. And the pollution degree 3 is pretty much industrial and farming, non-conductive pollution, but could become conductive due to expected condensation. Pollution degree 4 is pretty much outdoor applications. So you can see where why the server, telecom, and also for the automotive, they pretty much applies to pollution degree 2. And that is a very dominant thing. For some occasional cases, industrial is working pollution degree 3. For solar or some other, which can expose to very severe weather, you're going to apply the pollution degree there. And if you are sitting in a different, different locations of the office or the building, the impulse withstand voltage, or we call overvoltage category, also matters. I mean, if you're working on the category number 4, which is very close to the utility transformer, you got to see the highest impulse voltage. Category number 3 is pretty much your utility panel or distribution board. Category number 2 is outlets, which where your phone get outlets within your home. So you charge your phone adapter, laptop adapter. These are all go to the category number 2. That is the majority of server telecom OBC is being applied to, because it's being after the utility meter, is being after the utility panel. That is the category number 2 is the majority of our equipment been sitting at. Okay, so many parameters. How do these parameters been tested for the popular standard, which is IEC, VD, I'm showing right here. So basically all of this, you have multiple groups. Every group supposed to handle either mechanical or thermal or Creepage distance or lifetime. So every group have a purpose, but all the groups, most of the groups, like group 1, 2, 3, they have a precondition. What is the precondition? Test method B1, RIO, then it goes through all the tests, then they measure RIO, measure for the group 1, 2, 3, they measure RIO, and also partial discharge, method A. For group 4, it's testing the isolation resistance and the different temperature regions. Subgroup number 5 is just measuring the Creepage and then testing the flammability. For subgroup number 6, this is something I want to introduce. So only VD testing have it. IEC for the optocoupler does not have it, because this is the end of life test based on the high temperature working with the coefficient. And VD-10 is expired. Now we are all converting all of this certification to the VD-11. And the VD-11 is officially put in the TDDB right there, as you can see right here. So at this moment, all the TI parts that has been certified VD, we have -11. If you see a VD-10 there, we are updating the datasheet on the way. And UL 1577. So this is a tab test, it's a certification test, and it is slightly different with the testing before. And you can see here, this is not testing RIO, it's testing, okay, can my part handle, can withstand the voltage VISO for 1 minute? Not for 1 second, 1 minute, because in the production it's been tested 1.2 times the VISO for 1 second. Here it's testing for 1 minute, so then, okay, there's no isolation breakdown. For the double protection test, I want to tell you this is not double isolation. This is for certain applications which the UL has been specified into. And so far, I have not seen any applications which is using their part for double protection test. This is a very stringent test. I mean, you test the part under 20 kV, 500 nanoseconds, 50 cycle, 5-second interval, no visible damage. So at this moment, double test is not what I'm seeing very popular. So the majority is still the VISO we're tapping on the left. And it's also for the left, as long as the VISO has been reaching a certain level, it still can be called reinforced isolation. That is the key message I would like to reinforce right here. So now next stage, we learn all the parameters, all the standards. It's going to the system. What does the complete system requirement? Yes, if I'm building a converter, I want to make sure the component is good. I want to make sure that, okay, the component plus the PCB, which is every system standard built from IEC 664 have component and the system to make sure together going to the complete system requirement. So because of timing, I'm just giving an example for the telecom server. For other application, it'll be similar. And what is IEC 664 has been pretty much talking about? Okay, it has been talking about On low volt system, which is up to 1.5 kV DC or 1000 volts VAC, less than 30 kilohertz. It will tell us about the clearance and the Creepage distance under different voltage. It also testing about electrical strength testing. You want to make sure you have the package-wise, they are good. The capability-wise, you are good. So this is giving a guidance about the insulation requirements for majority of the end equipment. So this is the library. When you want to get something for your special equipment, you start from here. So this is a golden standard that a lot of end equipment are references to or borrowing from. And going to the IC 6064, there are so many pages, hundreds of pages. Which table matters the most? Table F1, F2, F4, and the correction factor, table A2. And they also show you how to do the electric strength test, either by withstand impulse testing or do partial discharge over working voltage. So if you summarize the 100 pages of A64, all of them are talking about this. So if you understand this table, you're pretty much close to where this table are telling you to. And dimensioning CRR, you have two ways. You have basic isolation, and for the F2, reinforced isolation for F2, but one step higher, which means, oh yes, if I want to building a reinforced isolation and look at F2 for 800 volts, then I go to one step higher. And here it shows many steps. You have 300 volts up to 12,000 volts. So which means reinforced isolation is just go one step higher. Not two times, just one step higher. If you're 1.5 kV transient, you go to 2.5 kV. If you're 2.5 kV, you go to 4 kV. If you're 4 kV, you go to 6 kV. That's why the impulse voltage in the datasheet has been spec in over voltage category 1, category 2, category 4. And here is an example, what I show, in the server telecom system. If your output voltage is not higher than 60 volts, this 60 volts we considered SELV, which is 60 extra low voltage, tied to the ground. You do not need reinforced isolation. You do not need. You only need basic isolation is good enough. And from the 60 volts to the 12 volts output, because your input is SELV, because the output is SELV, 60 extra low voltage, you do not need reinforced isolation. For here, most of the time, functional isolation will be good enough. That's why, a lot of customers are building a non-IC converter even right here, back boost. And you do not need a full bridge. Try to have more components and deal with the transformer. So here tells, you start from the SELV limit, and that limit has been listed in the equation here below. So it is SELV is 60 volts under than 60 volts DC, and the TNV means telecom network voltage. So if telling about if it is under 60 volts, then you have SELV or telecom network voltage category 1. If it's inside the building, you go to SELV, which is no. If it's outside of the building, it is TNV1. So if it's not SELV, then you go to hazardous voltage, which means you are pretty much above 120 volts. You go to 400 volts, it's hazardous voltage. And if it's yes, you go to TNV2 and TNV3. If it's outside of the building, it is TNV3. So this just tells you, which voltage category and why this voltage category matters. Here you go. Different voltage categories specify the IC 6950. Between each group, the isolation grade is being specified. And I put all of this table right here into the left-hand side table so that you can see for functional isolation only required between 250 extra low voltage, less than 60 volts brick module. For reinforced isolation, if you have a hazardous voltage to any other voltage, you need reinforced isolation. But if you are a 200 volts system, which is the TNV2, to other TNV-1 or -3, you only need basic isolation. So I'm giving you all the examples right here, so that when functional as needed, when basic as needed, when reinforced as needed. So all of them are not coming from, oh yeah, it's all been traced back to the standards or equipment. Okay, in each company we may have a few experts discuss, oh yes, it has been testing basic, or it's been for tens of years, it's always been reinforced. And no one even questioned why the reinforced is there. So here is the story which you can trace back to the fundamentals. And yes, as what we discussed, the IEC 6950 is talking about two things: clearance, creepage, and also with the mains transient voltage. As you can see right here, based on different AC mains voltage. For example, if this is being line to neutral, or if it is a single phase system, you have 120 volts, or in China, Japan, you have 240 volts. You only at different overvolt category, you are seeing the requirement is different. So, for example, if you are using a plug to your home, you only, for basic isolation, you only need 1.5 kV surge. And to go to reinforced isolation, oh, you go to one step higher. That's what you take out from this table. And also for over the 150 volts, this is including the higher voltage. Then you're going to have a higher step. So here, if you can see from 330 to 8 kV, it is all divided by different categories, which I illustrated in the stats before. So you can see, okay, what am I on my primary side voltage? What is my input? Okay, like in US, 120 volts. In other country, which is with the fixed voltage over than 120, see here up to 230, you use a higher grade. And next step is clearance. Okay, for peak working voltage, for example, and 420 volts, then you go if it is 1.5 kV transient, you only need 2 millimeter right here, and the value in the in the bracket applies based on the IEC 62368. This is a new standard, replaced IEC 6950. So this is for clearance and creepage. For functional isolation basic, for 400 volts, if you are working with a PCB with a material group 3A, you need 4 millimeter. If for reinforced isolation, please times 2. And now, oh, people say, okay, I need a reinforced isolation for driver. Yes, here you go. You need 80 millimeter. But when it's coming to the pulse voltage right here, it is not that high. I mean, sometimes we have a part which is pretty much very much overkill. So I'm giving some example which we can see right here. So I have this is a DC to DC. My output voltage is not 60 volts; it's reaching to 75 volts. So 75 volts is not a safety extra low voltage anymore. It is a TMV circuit. So if I'm going to my primary, going to TMV circuit, yeah, look in the table, I need reinforced isolation. And, you know, and for this system, I mean, the majority of the 40 volts battery are below 60. And there are some very legacy telecoms with nominal, not 48, it's nominal 60 volts. Is then reaching to 75 volts. But this, from the market-wise, the dominant is still SELV. Only to be compatible for some equipment go to over 60 on the max is very rare. And then you go to the table, you go to find the table. Oh, what is this? It's collapsing. Oh, sorry, let me open the slides again. That's been collapsed. We are here, and let's resume. So going to, if you search the table, say, okay, oh yeah, I'm over category number 2. I need 2.5 kV transient, and my clearance 4 millimeter. My at 5,000 meter, I need 6 meter because I need time 1.48. And if for the driver, yeah, you're pretty good. You're material group number 1, you only need 4 millimeter. But when you're in a PCB, you have to be times 2. And electrical strength test in the 3 kV ISO. So here you go. You know which package, and you need to choose what kind of electrical strength test the driver has to meet with. So this is one example of that's why the majority of the popular system that you see, is a wide body 8 meter, and they have to handle 44, 42, 42 peak, which is 3 kV RMS. And with that, I want to close the presentation with what here I have, what solution we are having now. So we have simple driver does not have. This is pretty much having the single channel like all on the here. We also have, this is a dual channel. I'm sorry. It's 21, 520, 530, 540, and also the 225 in LG package, 220 in narrow body package. They are all dual channel driver with very basic UVL protection features. We also have single channel driver, which UCC 53. Which is CMOS input. We also have optical compatible input. It's still CMOS isolation, but it's optical compatible input. It is 2351X family, and also have a lower isolation. 5 means 5 kV, 3 means 3 kV. So you can tell here. So these are all going to the simple drivers, single channel or dual channel. When you go to smart drivers, they're all single channels. All of them have DSAT, ready, fault, and for the 21.7 family, it have one additional sensing channel, which is you have analog signal in the temperature, voltage, or current. It can reading that signal with insulation barrier, give you a PWM signal. You can either with duty cycle or through RC filter. So 21.7 family give you additional next generation and fast for optimized performance with additional integration for traction drive and for high voltage motor power for silicon carbide for IGBT. It is the next generation of ISO 5451. UCC 5870 is TI's first HUD compliant and ISO 2626 compliant SPI with diagnosis with a 36-pin DWG package that has been targeted for automotive traction drives. With that, I think it's time for, thank you very much for your time, and we can spend the next 10 minutes, I want to say 12 minutes discussing the questions. Let me see what I got. And here is the final page. And let me see what question I got. Give me a second. Out of these. See what question I got. Okay, we do get a few questions. Let me see. Let me understand it. Okay, the second, one question is very interesting. What is the system test standard for automotive applications? So we, firstly, this presentation is part of the presentation I'm submitted for APEC 2021. So in June, I remember in June, I'm giving a 3-hour presentation for all the industry, discussing about server telecom, also discussing about automotive. And the automotive at this moment, there's no one standard based on my experience, and most of them is using IEC 60664. So that is what I can tell. Another question is what can I use to achieve higher voltage isolation, like 3.5 kV? It is not DC voltage, it's a pulse voltage. So what I can illustrate right here is the majority of TI driver. If you go to just for example in this table, as you can see right here, we have 5.8 family. This is the highest 1.5 kV reinforced isolation, and this is what this information showing here is working voltage. Okay, but let's see 5.870, 3.7 kV is not working voltage. This one is VISO, which is being spec in the datasheet. Another information I can tell is to read this table here. So that's why there are different parameters. If you want to answer your question, to handle a 3.5 kV pulse voltage, using the majority of our driver, even narrow body 4 mm, can handle 42 peak. Wide body can handle 80 peak. So I think that you can read in the VIOTM in the datasheet, you will find the right answer. Another question coming from Bernard, asking the slide number 17. Let me go to page 17. Is this profile for instantaneous DC voltage? Yeah, it is. This is a profile lasting for 60 seconds, and it is for peak volt. For the frequency, the asking frequency. It is frequency of 60 hertz. And yeah, when we are talking about VLTM is the peak voltage. If you can go to the definition of VLTM. So this is working voltage and the VLTM. VLTM is the peak value. VISO is RMS voltage. I see a few other questions is asking. Let me see. We have 7 minutes. Bernard, I wish that I answer your question, which we can talk more offline. Another one is, do we need to consider AC transient plus over voltage on the secondary side? Oh, I know what you're talking about. You're talking about 48 volt system. This is a long story. I have 20 more pages discussing that in the APAC. So please join APAC this year. And I can give some quick answer is we need trend for in this thing is 25 volts plus 75 volts. So you discussed about the 2.25 kV plus 75. Let me give you, it is not 25. If you test in your every equipment, you get 10% discount. So that's why it has 2250, 2.25. If you look into the brick model of the datasheet there, I'm 2.25 kV. The reason is it is 2.5 kV. It's been testing with a 10%. For every module, you get 10% discount. That is 2.25 kV. And to evaluate this one, you have two ways. Method one is for transient voltage. Another one is partial discharge test, which is based on working voltage. You have two ways to tell it. And all of this will be discussed in another presentation. It's a very good question. Is there any possibility of service resistance because of some parasitic inductance? Very good question. The answer is yes. It's talking about radiative immunity test. And we have collateral to supporting that, and the TI is doing extensive amount of tests. We are planning, for example, we have GND1 on the left, we have GND1 on the right, and we apply a very high frequency source, 1 gigahertz, try to switching the voltage, the peak from left to right, and to try to understand, okay, what is the internal resistance, which is we are discussing the conductive or radiative immunity, because if you go into the internal, go to the capacitor and transformer, they're all being developed in the OOK, how to say, on-off caning, and that is pretty much for the capacitor, because to transmit signal you can only apply high frequency, and then high frequency is roughly from 500 megahertz to a few gigahertz. Different manufacturer has been reaching at different times, but when you are going there, you're gonna see some kind of a noise being coupled, but that's why you have a differential amplifier, which is, you go to this page, you have two differential pair, and this is being designed to block any noise from left to right on the common mode. So because when you have radiating noise, it's pretty much common mode. So we have very good performance there too. Very good question. Another question: how do I arrive at VISO for system working voltage? How do I arrive at VISO for system? I don't quite understand what arrive means. The pros and cons if we replace existing design with ISO. What could be the pros and cons if we're replacing existing designs with isolated gate drivers? Okay. Firstly, I'll discuss in the cons. Cons is, yes, the ISO driver is relatively more expensive than non-ISO driver because it involving two die, it involving more bonding wires, it involving putting the die in the chip. It's all labor related. So all of this coming to assembly cost. So the cons is a little bit more expensive, but talking to the TI, FE, I want to see is with more vendors, more competitors coming to the market, ISO driver is being standardized for high performance converters. Everyone is using ISO driver to achieve high performance, better skew, higher CMTI, and what I can find now for every silicon carbide, gallium nitride, they are all using ISO drivers because of the performance. And for high frequency, you do not want to use opto because the jitter is, the jitter, the pulse distortion, the degradation of the LED, and all suffers a lot. So a lot of advantages. We here have a lot of collateral supporting them too. I found it strange SEL is 60 volt in electric industry, here I say 60, and guess telecom industry is different. That is, let me go into the industry. It's in 60 volts is being defined, and the server telecom, and because of 48 volts battery, 50 volts is being used for some labs. Below 650 volts, it is low voltage lab. So there are some differences, I think, that different standards being requesting. But 60 volts, I can tell you, no matter the AC6950 or AC62368, the new standards are all talking about 60 volts. So 60 volts in your design should be applied. That is my understanding.
I believe we have time for one more question.
Okay, thank you, Sean. Let me see. Okay, very good question. Do we need a slot in PCB beneath IC package? Yes, you do, and there's a requirement on the slot. We call it PCB grooving or PCB cutting. For different kind of material group, you cannot just cut. You need to cut with a certain width. Okay, for different material group, for different working voltage, they have a very strict requirement. If I remember correct, some of them with a different material group, with material group 3A, you are requiring at least 1 millimeter cutting. So some people may consider, oh yeah, I'm doing PCB cutting, I'm good. No, you're not good. You have to cut with at least minimum of a certain width. That is what if you go to the AC6664, they clearly define that. So make sure that you cut in with a certain width, and the reading going back to the standard. Make sure it is not cutting half meter, not cutting a quarter millimeter. It's cutting a 1 millimeter, or depending by the material group you are sitting at. So with that, I think we are perfect, and for sure, asking questions in the E2E, TI E2E, and reaching to our field application engineer for more questions. I really appreciate your time and the questions, very good questions online. And also thank you, Sean, for helping us to moderating here. Thank you, everyone, and I will talk to you soon. Probably see you in APAC 2021 in June. Bye-bye.
Thanks, Wei. And thanks, everyone, for joining. So just for everyone's information, the recording of this session, as well as the presentation, will be available later this week on ti.com/high-voltage-seminar. You'll also receive an email with links to the on-demand presentation and a post-event survey. If you have time, please provide feedback so we can continue to improve our content for the future seminars. Again, thanks to Wei, and thanks for everyone for joining, and have a great day.
Bye-bye.